everyone, and welcome to this explainer. If you're staring down an upcoming technical interview, you know for a fact that sorting algorithms are practically guaranteed to come up. Today, we're going to demystify this incredibly dense, but totally invaluable sorting algorithms cheat sheet. We're taking what looks like a giant wall of text and code, and we're transforming it into a logical, easy-to-remember toolkit so you can confidently go in and absolutely crush your next interview.
Okay, let's dive right in with a classic interviewer hook. Which sorting algorithm should you choose? Now, we've got to acknowledge right out of the gate that there is no single correct answer here. Answering this question correctly depends entirely on knowing your specific constraints. You just can't pick the right tool without knowing the parameters of the job, right?
So before we look at any specific algorithms, we've really got to define our ground rules. These are the actual constraints interviewers care about. Let's start with stable. As the cheat sheet highlights, a stable sort simply means that if you have equal elements, they maintain their original relative order after the sorting is completely done.
We also need to wrap our heads around in-place sorting. The source defines this as sorting done without using extra memory space, which is typically represented as big O of 1. The absolutely crucial takeaway here is that this is a vital metric when your system's memory resources are strictly limited. All right, here's our roadmap for today. First, simple sorts for small data. Second, the efficient heavyweights. Third, non-comparison-based sorts. Fourth, the master comparison table. And finally, cracking your technical interview. Let's get into it.
Section 1. Simple sorts for small data. As a general rule of thumb, these simple sorts usually hit an average and worst-case time complexity of O of n squared. They're super easy to understand, but they really don't scale well. First up is bubble sort. The core idea here is to repeatedly compare adjacent elements and swap them if they're in the wrong order, so the largest elements effectively bubble up to the end with each pass. Now, while it is stable and in place, the cheat sheet explicitly notes its primary use case. It is strictly best for simple problems and small datasets. That O of n squared average time just makes it way too sluggish for anything larger.
Next is selection sort. This algorithm scans the unsorted part of your data, finds the minimum element, and just drops it at the beginning. But notice the major trade-off here. It's in place, which is awesome for memory, but crucially, it is not stable. The cheat sheet advises it's best for small datasets, specifically when memory swaps are costly.
Rounding out our simple tier is insertion sort. You literally pick an element and insert it into its exact correct position in the already sorted left part of the array. It's stable, it's in place, and it's highly recommended for small or nearly sorted arrays. In fact, if the data is already mostly sorted, its best case time drops all the way down to a blazing fast O of n. Moving on to section 2, the efficient heavyweights.
Now let's raise the stakes a bit and move into the big leagues. Before even thinking about code logic, consider the massive leap in mathematical efficiency here. We're dropping from that sluggish O of n squared down to O of n log n for average scenarios. When you're dealing with millions of data points, this difference is the exact reason why these heavyweight sorts even exist. Our first heavyweight is merge sort. This uses a totally brilliant divide and conquer strategy. You divide the array into halves, recursively sort those halves, and then merge them back together. This guarantees O of n log n speed even in the worst case, and it remains a stable sort. But of course, there's a trade-off. It's not in place. It actually requires extra memory space equal to the size of the array. So it's best used for large datasets and external sorting. Then we have quicksort. The idea here is to pick a pivot element, partition the array into elements smaller than the pivot on the left and larger on the right, and then recursively sort both sides. Quicksort is a general-purpose powerhouse that the cheat sheet calls the fastest in practice. But beware, if you pick a bad pivot, its worst-case scenario degrades into an absolute nightmare O of n squared. Also, while it is in place, it's not stable.
The final heavyweight is heap sort. Here, you build a max heap data structure, and then repeatedly extract the maximum element to form your sorted array. Heap sort gives us that sweet, guaranteed O of n log n speed while being entirely in place. This makes it the absolute perfect choice when extra space is strictly limited. The catch? It sacrifices stability to pull this off.
Section 3. Non-comparison-based sorts. All right, let's introduce a little plot twist. Up until now, every single algorithm has compared elements against one another. But let's look at algorithms that completely break those rules. First is counting sort. Instead of comparing, you literally just count the frequency of each element and then place them in order based on those counts. Because it avoids comparison entirely, counting sort boasts an incredible time complexity of O of n plus k, where k is the range of elements. But it's highly specialized. It's really only best used for a small range of integers, and it does require extra space.
Building on that non-comparison concept, we have radix sort. It takes things further by sorting numbers digit by digit, starting right from the least significant digit. It's a stable algorithm with a time complexity of O of d times the quantity n plus k, where d is the number of digits. This makes it absolutely exceptional for sorting large numbers or strings, though, just like counting sort, it's not in place.
Section 4. The master comparison table. We've covered a ton of ground, so let's bring all these disparate threads together to look at the ultimate cheat codes derived straight from the source's comparison table. When we isolate the time complexity data, you can clearly see the tiers. The simple sorts drag at O of n squared in average and worst cases. But then look at how the heavyweights, merge, quick, and heap sort just dominate the middle of the pack with super reliable O of n log n average performance. And right at the bottom, the non-comparison sorts break the mold entirely with linear-like speeds. But when we shift our focus to the constraints columns, well, that's where we see the true trade-offs. Fast algorithms almost always demand a sacrifice. Blistering speed, like in merge sort or radix sort, often cost you extra space. Or in the case of quick sort and heap sort, it costs you stability. Understanding these compromises, that is exactly what separates a junior developer from a senior one.
Section 5. Cracking your technical interview. We have finally reached the finale. It's time to translate all this dense theory into actionable, rapid-fire rules for your next interview. The cheat sheet lays out these direct, no-best rules, and honestly, you should memorize them. Merge sort is your go-to for stable, large data or linked lists. Quick sort is your default because it's fastest in practice. Heap sort is your absolute savior when you need to save space or use priority queues. Insertion sort is your secret weapon for nearly sorted data. And counting or radix sorts, those are your magic tricks for integers in a limited range.
The single most important takeaway of this entire explainer is right at the bottom of the cheat sheet. Before you write a single line of code on that whiteboard, you must ask the interviewer about constraints. You've got to ask, do equal elements need to stay in order? What are our memory limits? Choosing an algorithm really isn't about knowing which one is best. It's about knowing which one is best for the environment you're in. So I'll leave you with this final thought. Look at the code you're writing today in whatever product you're currently working on and ask yourself, are you actually using the right algorithm for your specific constraints? Or are you just using the one you're most familiar with? Think about it. Keep learning, keep asking those questions, and you are absolutely going to crush that interview.